Today we are going to see the performance of the experiment to study the effect of time on the rate of crystallization. So the requirement for this experiment is we are going to require lot of beakers, funnel, conical flask, glass rod, etc. In chemicals we will require water, boric acid, and in equipment we are going to use microscope, stage micrometer, and eyepiece. So crystallization is the natural or artificial process by which solid forms, okay, means there occurs the generation of solids from the liquids. Okay, so here the atoms of the molecules, they are highly organized into a structure. Okay, so we can say the crystal lattice, it starts to take place, it occurs during the process of crystallization. Okay, so it gets oriented, the atoms, they get oriented into a specific dimension, okay, to give rise to a crystal. So some of the ways by which crystals form are precipitating from the solution. Then you can also carry out crystallization by freezing, or very rarely by deposition directly from the gas. Okay, so these are the two methods, either by precipitating or by freezing. So attributes of the resulting crystal, it depends largely on the factors such as the temperature, air pressure, and in case of liquid crystals, it depends on the time of the fluid evaporation. So we can say the factor like temperature, air pressure, time, also the concentration of the solute in the saturated solution, it determines the rate of crystallization. So crystallization, it majorly occurs in two steps. The first step is the nucleation. Now the name itself is suggestive. Nucleation means here the first nuclei, it will it will be formed, and that nuclei, it will directly determine what will be the shape and characteristic of the um, crystal. Okay, so the appearance of the crystalline phase from either a supercooled liquid or a saturated or a supersaturated solvent. This is the first step. The second step is known as the crystal growth. Right, now once a nuclei is formed, suppose this is your nuclei, then what will happen in crystal growth? Just the material which is present in surrounding solution, it will come and it will start to deposit in the same orientation as that of the nuclei, right? So here just crystal growth is going to occur. That means we can say this the thickness, and the size, it will increase. Okay, so which is the increase in the size of the particles, and it leads to crystal state. Okay, so the nuclei, they are very delicate. If you stir the solution, okay, which contains the nuclei, then there is a chance that these nuclei, they might get dissolved once again. Okay, so nuclei formation is the most critical step. Okay, and it is very important step. So the importance of the step of crystal growth is that the loose particles, they will form the layers at the crystal surface, and they will lodge themselves into open inconsistencies such as pores, cracks, etc. So the crystallization process, it consists of two events, nucleation and crystal growth, which are driven by thermodynamic properties as well as chemical properties of the solvent as well as the solute. So in crystallization, nucleation is the first step where the solute molecules or the atoms which are dispersed in the solvent, they start to gather into the clusters, but this happens on a microscopic scale. Okay, so elevating the solute concentration is so what is this formation of nucleation? It is the elevating of the solute concentration in a small region. Okay, so after some time it becomes stable under the current operating condition. So these stable clusters, they constitute the nuclei. Therefore the clusters need to reach a critical size in order to become stable nuclei. Such critical size is dictated by many different factors which we have discussed, like temperature, supersaturation, means concentration of the solute in the solvent. So it is a stage of nucleation that the atoms of the molecules, they arrange in a defined and periodic manner. Okay, that is the crystal lattice. Okay, it starts to form at the very basic stage of nucleation. Okay, so this lattice, it defines the ultimate crystal structure. You have to, it is very important that crystal structure is a special term that refers to the relative arrangement of the atoms or the molecules, and not the macroscopic properties of the crystal like size and the shape. Okay, so these shape and size, these are the result of internal crystal structure. So the crystal growth is the next step. It is a subsequent size increase of the nuclei that succeed in achieving the critical cluster size. So crystal growth is a dynamic process, we can say. It occurs in equilibrium where solute molecules or the atoms, they will precipitate out of the solution and dissolve back in the solution. So supersaturation is one of the driving force for the process of crystallization. Even if you carry out crystallization by any two method, that is precipitation or freezing method, so what happens here? The solution, it becomes so saturated with the amount of the solute that no further solute it can go into that solution form, right? It cannot dissolve. So by evaporation or by freezing or by precipitation method, what we are doing, we are producing a supersaturated solution. So we can say, so it is that the supersaturation, it is the only driving force for crystallization. So depending upon the conditions, either nucleation or growth, it may be predominant over the other, dictating the crystal size. So we will see the performance of the experiment now, and then we will discuss the observations.
Going to see how are we going to perform the practical. Okay, so first what we are going to do, we are going to prepare a supersaturated solution of boric acid. Now how a supersaturated solution is formed or produced? So we take some amount of water. So for today's experiment we are going to take 200 ml of water. Into it we will slowly add boric acid until all the boric acid gets dissolved, right? Now after that we will still add some more amount of boric acid until the boric acid it does not get further dissolved into that water. So that forms our supersaturated solution, right? Then afterwards, once our supersaturated solution is formed, then we will filter it using the filtering assembly, and that filtrate is our supersaturated solution, right? So that supersaturated solution, we will divide it into 6 parts. Okay, 6 parts, 30 ml, we are going to divide it into 6 parts. Okay, those 6 parts we will keep it for 10 minutes. One part we will keep for 10 minutes, next part we will keep for 20, next for 30, then for 40, then 50, and then 60. Okay, for 1 hour we are going to do this practical, right? So what we have to do, we have to allow that 30 ml to cool down for 10, 20, 30, 40, 50, 60 minutes, and then we will filter out that solution, and we will measure the particle size of the crystals which are formed at 10 minutes, 20 minutes, 30 minutes, 40 minutes, 50 minutes, and 60 minutes, right? Now that particle size, from analysis of that, we will come to know that what is the rate, what is the effect of time on the rate of crystallization, right? So now we will proceed with our practical. So we have taken this boric acid, and we will add some amount of boric acid directly into this previously measured 200 ml of water. We will dissolve this boric acid until we get a supersaturated solution. See, now the boric acid had got dissolved. Only small lumps are remaining, but those will also get dissolved. So still our supersaturated solution is not formed yet, we can say. We might need to add further a small amount of boric acid. now as you can see here, after addition of again small amount of boric acid, now this boric acid it no longer gets dissolved, and the solution now, if you can observe here, it is not clear but it is turbid. Why? Because the boric acid it has not dissolved completely, right? So we have attained our supersaturation level. Okay, so now to remove the excess undissolved boric acid, we are going to filter it. Now you can see we have received here a clear filtrate. Now why it is clear? Because the undissolved boric acid that has filtered out. Okay, but this solution, it is highly saturated solution of boric acid. Once we will obtain the filtrate, then we will divide this filtrate into 6 parts. Now complete filtration has occurred, and we will divide this filtrate into 6 parts. Okay, 30 ml we are going to pour into each of these beakers. We have labeled them as 10 minutes, 20 minutes, 30, 40, 50 and 60. So we will take 30 ml into each of these beakers. So this is our 10 minutes. We have started the time. We will wait for next 10 minutes. We will keep these beakers into cool water, okay, and then we will wait for 10 minutes. After 10 minutes, we will take out the sample and we will measure its particle size. Now to measure the particle size, we are going to use the process of micromeritics, that is optical microscopy we are going to use, okay. So in that we use a stage micrometer and we use eyepiece, right? Now if you look at the stage micrometer, there is a scale of 1 mm, okay. This 1 mm scale, it is divided into 100 parts, okay, or 100 units. So the 1 unit of this stage micrometer is equal to 10 micrometers, right? Then the eyepiece, on the eyepiece, the scale of 10 mm, it is 0.1 mm, right? So now when we calibrate this eyepiece with the stage micrometer, the stage micrometer is used for calibration purpose of this eyepiece, right? Now what we are going to do, we will place the stage we will place the stage micrometer on the stage of the microscope, and we will place the eyepiece, okay, in the eyepiece holder. So we will coincide the two lines of this eyepiece with the two lines of the micrometer, and we will calculate which unit coincides with which unit number with the stage micrometer. Okay, now I am going to show you how we are going to do this, but our stage micrometer, okay, our eyepiece, it shows the calibration that 8th line of stage micrometer, it coincides with 6th line of eyepiece, right? Now how will you say, how will you calculate the distance between the two lines of the eyepiece? So the formula is one line of eyepiece is equal to 8 into 10 divided by 6. Okay, this is for our stage micrometer. So this answer comes to 13.3 mm. So we can say the distance between two lines of the eyepiece is 13.3 mm. Let me correct, it won't be mm, it will be micrometers. Sorry, that was my mistake. So the distance between two lines of the eyepiece is 13.3 micrometers. So now as you can see, this is the microscopic view. Okay, so the 6th line of the eyepiece, it is coinciding with the 8th line of the stage micrometer, right? Now we will see the remaining practical. So we have calibrated our eyepiece. Now you can see here, this is our 10 minutes sample, and if you observe the sample carefully, then we have got the crystals here, right? Okay, now we will take some small amount of this crystal on our glass slide. We will cover it with a cover slip, and we will determine the particle size with the help of the eyepiece. Okay. So now you can see these are the crystals which are formed in the first 10 minutes. Okay. So we have calculated the average size, and the average size of one crystal, we can say, is 18 units of the eyepiece. So now we will take out the 20 minute sample, and now see, just have a look at the crystals. You can see the crystals. Okay, so very nice crystals are formed. Now again we will take out some sample on the slide of these crystals, and we will, with the help of cover slip, we will cover it, and we will see the crystal growth. Now as you can see here, the crystals, they are very well formed. Okay, and we have determined the average particle size of the crystals, and it was found to be 27 units on the eyepiece. Okay, now we will proceed for the 30-minute sample. Now this is our 30-minute sample, and if you can see here, if you observe the crystals are very well formed. So now these are the crystals which are formed at 30 minutes. Okay, so the average size of this crystals is 36 units of the eyepiece. Now we will proceed for the 40-minute sample. So now this is the sample of our 40 minutes, and if you can observe this crystals growth, okay, it is just great. Okay, now we will take out some sample and we will proceed with the determination of the particle size. Now we will place a cover slip and we will check the size. So now these are the crystals at the end of 40 minutes, okay, and the average length was found to be 48 units of the eyepiece. Now we will proceed for the 50-minute sample. Now this is our sample for 50 minutes, and just look at the growth of the crystals. Okay, now again we will check its size using the stage micrometer. So this is the crystals for 50 minutes. Okay, the average particle size of the crystal was found to be 60 units of the eyepiece. Now last we will wait for some minutes and we will proceed for the particle size determination for 60 minutes. So now we have completed our 60 minutes and this is the sample for the last 60 minutes. Just look at the crystals. The growth is very nice. Now we will take out some sample, we will put it on our slide and we will determine the size. So these are the crystals for the last 60 minutes and the average particle size determined was 78 units of the eyepiece. Now we will proceed with the observation table. Now let us see the observation table. Okay, so the observation table is very simple. The first column, it consists of the time. Next is the particle size which we have detected using the eyepiece, and then what is the actual particle size. Okay, as we have seen, the calibration of the eyepiece is 13.3 micrometers. Okay, so what we are going to do, we will multiply 13.3 with these values. Okay, and that will be the actual particle size, or that will be the actual crystal size, right? And it is given in micrometers. So when the time was 10, at 10 minutes, particle size on the eyepiece detected was 18 units, and hence we can say the particle size is 239.4 micrometers. At 20 minutes, it was 359.1 micrometers. At 30 minutes, it was 478.8 micrometers. At 40 minutes, it was 638.4 meters or micrometers. At 50 minutes, it was 798 micrometers, and at the completion of 1 hour, it was 1037.4 micrometers. Okay, now by just mere observation of this table, we can say, as you allow time to proceed, okay, you allow the procedure of crystallization to proceed, the crystal growth or the size of the crystal, it goes on increasing, right? So in the result, we will just report, as the time period given for the process of crystallization increases, the size of crystals, it will also go on increasing, right? Now let us see what are the commonly asked questions about this experiment. The first very commonly asked question is, what are the two steps of crystallization? We have already discussed, one is nucleation and the second one is crystal growth. Then definition of crystallization, then what are the different factors which affect the process of crystallization. Then polymorphism is also a term. Okay, polymorphism means the particle, it has got same chemical structure, but only the arrangement of the atoms in that different polymers is different, right? And as the arrangement of the molecules or the atoms is different, one polymer, it have um, characteristics, physical characteristics different than the other polymer, right? And the last question will be, what are the two methods of crystallization? So it can be freezing, or it can be precipitation method. Okay, so these are the different methods. So this was all about the experiment. Thank you for watching.